Now, before we get to the statement of the quotient-remainder theorem, what I'd like to do is introduce a little bit of vocabulary for the different quantities that we have running around this problem. So in the previous set of slides, we were talking about A, which was the number of watermelons we could use for that value, which was the large number of objects, is the dividend. We then had a value we were using the variable B to represent, which was the number of hippos, and we could think about that number as being what's called the divisor. So we've got the dividend over here, the things to be divided up, and the thing doing the dividing is the divisor. But there are actually two other quantities in this problem that will be of importance to us. There is something called the quotient, which is the number of watermelons. The quotient was sort of like the solution. That's the number of watermelons that each hippo has, or speaking more generally, it's the number of things in the group, in each grouping. And then there was one additional value, which is the number of leftover objects, number of leftover watermelons. And as is indicated by using that letter R, that value we are going to call the remainder, the number of things that remains, the number of leftovers. So those are your four vocabulary words: dividend, divisor, quotient, remainder. And with those vocabulary terms, we're ready to state the theorem, which is the main purpose of this collection of videos, that I call the quotient-remainder theorem, again, sometimes called the division algorithm. And here we're going to see the manifestation of all of those criteria that I asked you to think about in the previous video. So here we're going to lose the watermelons and hippos example. Very sorry about it. We'll refer back to it after we've stated the theorem generally. We're just going to let A be any old integer, positive, negative, or 0. It's some sort of object to be divided. We're going to have a different kind of restriction on the divisor, which we were denoting by B, number of hippos. We're going to make that integer be positive. If we make those kinds of assumptions, that A is an integer, a whole number, positive, negative, or 0, and B is just a plain old positive integer, then there are actually unique integers Q and R, Q for quotient, R for remainder, that have the following two properties. The first is that the remainder has to be strictly less than the divisor, but it could be equal to 0. The second requirement is that the dividend is equal to the quotient times the divisor plus the remainder. And those things together make up the quotient-remainder theorem. Now, what I'd really like to do is walk through all of those restrictions and give a little bit of context for them. So the first restriction is that A needs to be an integer. We're only dealing with integers with this quotient-remainder theorem. Even if we change the context, we're going to think about whole numbers of things. However, we are going to allow that integer to be negative or 0. If you want any justification for thinking about why maybe we would let the number of things to divide be negative, I really like to look to examples for debt for that. So I think about a whole bunch of friends going out to dinner together and they have to split the bill, and the bill is the thing to be split up, and those are debts that need to be paid. So we can think about the number of things to be divided as possibly being negative. However, the B is representing groups of things. We're going to have this many groups of things, and then we're asking how many things go into each group. Groups of things is always a positive number. It maybe makes sense to think about 0 groups of things, but I'd encourage you not to think about that because thou shalt not divide by 0, and we're doing division here. And so we're going to want to have groups of things. We're not going to think about having 0 groups of things. We're just going to think about taking some integer and putting it into some number of groups. Number of groups really ought to be a positive number. Now, in terms of the quotient and the remainder, they're also going to be integers. Everything involved here will be integers, but the real stickler on this condition is we are going to have a remainder, and there is a relationship between the number of things that's left over and the number of groups that we have. If you'll remember that one of our restrictions was that we wanted to be very greedy, we wanted to give as many watermelons as possible to the hippos. Well, if we had a remainder, enough left over that was greater than or equal to the number of groups, then we haven't really accomplished the greediness of using as many of the objects as possible. Every one of those B groups could have at least one more thing in it, and therefore we wouldn't have satisfied that criteria that we have. So look at this inequality here. It's okay for there to be nothing left over. In fact, that's the easiest example that we presented first. What if I had 36 eggs and I want to know how many dozen? Well, that would be great. There wouldn't be anything left over. Not having anything left over is okay, but you must have fewer things left over than the number of groups you have, or you haven't done your job properly. So that's the quotient-remainder theorem, a theorem that's really important to us that we'll use repeatedly as we learn abstract algebra. Now, what I'd like to do is just maybe bring this new theorem that we're learning back to the definition of divisibility way back when in a discrete structures class, or when you were learning about what is the definition for one number to be divided by another number. Let's go back and say that we have an integer a. We're going to say that it's divisible by, again, a non-zero integer b. Don't want to divide by 0. If there exists a third integer, when I teach it in discrete structures, I would call that integer k. Here we could call it q if we really wanted to stress its relationship with the quotient-remainder theorem, for which we can write a is equal to the b times the k. In other words, if we had that plus r there, the r would be equal to 0. There wouldn't be anything left over. And that again goes back to our example with the eggs. If I had 36 eggs and I wanted to know how many dozens that is, there wouldn't be any eggs left over when I do this division process. Another thing I want you to remember is that at some point when you were learning to write formal mathematics, you should have learned a handful of symbols for various sets that can be useful in a shorthand, so we don't have to write an integer, a non-zero, an integer, another integer. It's a lot of words. So sometimes when we want to just denote the set of integers, we use this z, this bold-faced z, to denote the integers. And with this definition comes one more thing that we can do, which is to relate that quotient-remainder theorem back to our definition of divisibility. So suppose that we have two integers, a and b, where b happens to be a positive integer, so we can make reference to that quotient-remainder theorem because that was a criteria here. Then a is divisible by b if and only if a has a remainder of 0 when divided by b. So that's what we were talking about up here when I said imagine there's a plus r. This is the case where the r is equal to 0. All this little lemma is doing is giving us a direct relationship between the quotient-remainder theorem and an old definition that we know and love.